Hello everyone, my name is Jameela. I'm a second year PhD student at York University, Canada. I will be presenting my research simulation-based data augmentation using physical priors for noise filtering deep neural network. I will establish the background and motivation of this research. We will discuss proposed methodology, our experimental results, and the discussion of these results and the conclusion that we have driven from our research. LiDARs have been adopted as primary sensor for mapping natural and built environment. There are three types of LiDARs: airborne, terrestrial, and satellite LiDARs. Traditional LiDAR systems send a laser beam towards a target and wait for the reflected beam to come back. The opportunity time window for a reflected beam to come back was won by PRF. PRF is an important configuration of a LiDAR, which is known as pulse repetition frequency. As the technology was advancing, the PRF was increasing and it was becoming impossible to get a signal back in the time window. To overcome these problems, multiple pulses in air technology was introduced in 2006 and was commercially adopted by various manufacturers in 2007. All the manufacturers developed a proprietary algorithm for matching sending and receiving pulse. Because the multiple pulses in air technology enable LiDARs to keep sending the laser pulse without waiting for the pulse to come back. There are a lot of pros of this new technology. There are no blind zones anymore. As you can see in the images, the point clouds are very rich and dense. The system is cost effective and the surveys are faster, but it's also vulnerable to atmospheric returns. As you can see, most of these atmospheric returns are projected either on the ground or overlapping with the objects of interest, hence compromising the perception quality of the scene. There are multiple noise filtering networks already exist in the market or used academically, but none of them deals with large-scale point cloud or complex and clump noise points. So to deal with that, there's a need to develop a noise filtering deep neural network. But this noise filtering deep neural network will require massive amount of diverse and annotated dataset, which is very expensive to deal with. To overcome this problem, we decided to develop a simulation. We developed a simulation using physical priors and Gaussian generative functions. We proposed two methodologies. One is based on LiDAR physics, the other one uses the LiDAR physics and Gaussian generative model. Physical prior-based simulation is largely based on LiDAR physics and generator noise, which is not closer to the real dataset. The Gaussian-based model simulation generates noise closer to the real dataset by utilizing the physical priors and Gaussian generative functions. The mathematical model for Gaussian-based simulation is pretty simple and straightforward. It calculates the maximum distance traveled by a laser beam before the next one is fired, and then a Gaussian generative function calculates the range of different synthetic noises and help us project them on the point cloud. Our first experiment is an ablation study between SVM denoising autoencoder PointNet and 3D UNet, which is a voxel-based 3D CNN network. While the second experiment is a 3D UNet simulation-based data augmentation experiment, which we use a training set including real data set and synthetic data set generated by GM simulation. Our ablation study clearly shows 3D UNet performing better than all other methods. Noise filtering experiments with and without augmentation shows better performance for augmentation cases. Visualization shows that the augmentation works better for the cases which have more overlapping noise. Our research and analysis shows the physical priors along spatial distribution provides leverage for simulating synthetic datasets, and also the vertical geometry and the global and local spatial distribution of noise points is very important and plays a vital role in designing any noise filtering algorithm. The long tail data distribution problem or imbalanced data set can be addressed using simulation-based data augmentation.